Good morning and good afternoon. My name is Egecem Kırcı and I'm from ETH Zurich. Today, I'll be presenting our work, Five Blind Men and the Internet Towards an Understanding of Internet Traffic. This is joint work with Ayush Mishra and Laurent Van Bever. Let me start with a simple observation. Imagine you're a network operator. Traffic shapes your decisions. Where should you be present? Where should you peer? These are the types of decisions that are about topology design, and they depend on knowing which regions in the world are growing or are becoming the hotspots. How much should you provision your bandwidth? When should you upgrade your links? These questions are questions concerning capacity planning, and it requires a knowledge of how fast the traffic is growing, and especially over extended periods of times. How do you balance your traffic load throughout the day? How do you avoid congestion? These questions concern traffic engineering, and it means knowing the shape of your traffic, or the shape of the traffic in general, when it peaks and when it dips. So these questions matter at every scale, but when it's about your own network, they are usually manageable. But what about the internet as a whole? Unfortunately, or fortunately, the internet is massive, federated, and diverse. But this also means that we don't see all the traffic in the internet, and probably we never will. So what do we do to understand more about the internet traffic? We piece together whatever we can. We check dashboards from platforms such as Cloudflare Radar or from Google. We use data from transit networks such as GEM, or we use the estimate figures or white papers coming from vendors such as Cisco or Sandline. But the problem with that is each of these vantage points have their own blind spots. Platforms like Cloudflare see a vast amount of traffic, but it's their own traffic. It's not application agnostic. Transit networks see a mixture of all traffic, but they are usually regional. This traffic doesn't come from the whole globe. Or the vendors usually claim reach, global reach, but their methodologies are not necessarily verifiable. So you can check their numbers or estimates in their yearly reports, but you can't really reason about how they reach those numbers. And ultimately, each one of these vantage points see a different part of the elephant, as in the parable of the elephant and the blind man, not the whole thing. So what we ideally need is another blind man. That's a complementary vantage point to the other alternatives that we discussed. One that's ideally application agnostic, that sees all kinds of traffic, globally distributed, that gets its data from all around the globe, and verifiable in its sharing practices or the methodology of how it collected the data. Our thesis is, and our paper is about that, internet exchange points are exactly this kind of a vantage point. Why? First, they have visibility into all kinds of traffic, not just one application, not just one provider or one network, traffic that comes from many networks and many services. Second, they are globally distributed. IXPs exist in many countries around the world, indeed most countries, and they are a cornerstone of the internet architecture. So they are almost everywhere. And third, they have an incentive to share their traffic statistics because more traffic attracts more members. So IXPs tend to publish their traffic statistics rather openly. Of course, IXPs also have their own blind spots. For instance, they don't see private interconnects. That is the traffic that's exchanged between two networks and not over the public exchange fabric of IXPs. And also, they don't tend to report flow level granularity. So when they report, we only see the aggregate volumes of the exchanging fabric, public exchange fabric of the IXP. And also, since it's not flow level, we don't see from which provider this data comes from or where it goes, where it comes from, details like that, only the aggregate numbers. But eventually that's the point. Like the other blind man, IXPs are just touching a different part of the elephant, and they are basically complementary. They are not an all-in solution. So if you think that IXPs are the right kind of vantage point to collect data from, someone needs to actually collect the data. That's what we do in this paper, and it wasn't trivial, technically. First, we had to find all the IXPs that exist in the world, and the subset that actually is willing to share, is sharing traffic. For this purpose, we went to PeeringDB, which is a meta directory for IXPs, and got the list of all the IXPs in the world. And from this superset, we manually looked into the web and found the subset of IXPs that publicly share their traffic statistics. Once we identified these IXPs that actually share their traffic, we saw that we should also find a way to handle all these heterogeneous data formats. Because in some of their networks, it was JSON APIs. In other websites, it was HTML embeddings. In other cases, they were just images, and we had to OCR the numbers from inside the images. So we built scrapers for each individual case, and we started collecting this data every 5 minutes. The third thing was we had to keep doing this reliably. The framework's supposed to run continuously every 5 minutes, and it's actually been running for years now. To achieve this, we had to implement a redundant framework such that when a node fails, the other nodes could be keeping on collecting the traffic, and individual physical problems doesn't cause any failures in the totality of the system. For the system details, you can check out our paper. We have more details about that. So the result of this collection framework is 2 years of data. Our paper actually analyzes data from starting of January 23 to end of December 24, so it's two full years. We have a little less than all the IXPs that are recorded in PeeringDB. We have 472 IXPs actually that we collect traffic from, and it's just from all around the world. And we've been collecting for a 5-minute granularity, which is the standard way of sharing these numbers. By late 24, we were seeing 300 terabits per second of peak aggregate traffic in the globe. So as I said, 472 IXPs are a little less than all the recorded IXPs in PeeringDB. But what actually matters is not the count of how many IXPs we collect from, but their traffic coverage. And as we'll see in a couple of slides, we are confident that we are collecting the majority of traffic of the IXP ecosystem, although the number of IXPs are around half. To our knowledge, this is the largest public data set of IXPs ever assembled. And the framework, as I said, is still running, and the data is publicly available for anyone to use. Having learned about the data set, the natural question is, can we trust this data? Since this is a longitudinal study, we have been tracking our port capacity coverage over time against the total port capacity coverage of every registered IXP in PeeringDB. So when we check this number, we see that stably over the 2 years, we have been collecting around 87% of global IXP port capacities in the world. So we've been collecting data from IXPs that correspond to 87% of global port capacity coverage. This has been relatively stable, more or less over the 2 years, and still going stably, even after the data set that the paper talks about, into the 25. And the fact that we collect a majority of the port capacity, we have visibility into a majority of port capacities, tells us that there's probably confidence into the amount of traffic that we've been collecting is also more or less around those levels. Another thing is that there's this 87% of capacity coverage globally, but if you look into it regionally, and these regions are defined as how the PeeringDB defines them, we have at least 80% port capacity coverage in each region. So not only we have a good coverage globally, but we believe we also have a good coverage of the IXP ecosystem regionally. So we have a data set that's global, longitudinal, and representative. What does it actually tell us about internet traffic? So over those 2 years, starting from 23 to end of 24, we observed 49% traffic growth in global IXP traffic. But can we really trust this number? We compared our trends against Cloudflare Radar's global reports. In 2023, we measured an global increase of 23.4% growth, and Cloudflare reported 25%. So it's relatively close. In 2024, we saw a 16.9% increase, and they reported 17% increase, which is almost the same. So in our analogy of five blind men and the elephant, this is basically the blind man agreeing. When two independent vantage points see those same trends, let's say, our confidence in both of their reportings goes up. But we also see that 49% of global growth hides 7 different realities if you look into it regionally. Let's look at the regional breakdown. As you see, Asia Pacific by far has the biggest increase. Their traffic actually over those 2 years more than doubled. The Middle East and North America saw an increase around 70 to 80%. And Africa and South America saw an increase around 6 to 7%. Australia stands at around 43%. And Europe, by far having the largest amount of traffic among those that we collect, sees actually the smallest amount of traffic rise in just 16% over 2 years. So if you look at the volumes that we actually collect, we see that the traffic we collect is heavily skewed. Europe alone accounts for nearly half of all the traffic that we collect. That is around 70% terabits per second on average, and also on average over 2 years. But is that really a measurement bias? We don't think so, because our port capacity coverage exceeds 80% in each region. We believe this skewness is probably likely reflecting the real distribution of how much traffic IXPs see in each region. So we believe European IXP ecosystem is also way larger than the others in terms of the traffic that they see. So growth tells us how much traffic is increasing. But going back to our motivation, what about the shape? When does the traffic peak and when does the traffic dip? In our analysis, we found that around 10 to 15 gigabits per second, it's enough to start seeing clear patterns, and patterns emerge from basically noise. And in this figure that you see on the slide, you basically see the evolution of how patterns are emerging depending on how much average traffic we see. So every region in our dataset clears this threshold of 10 to 15 gigabits, actually clears it by far. And so we believe the patterns we will be analyzing next are also representative of the regional traffic. Let me show you 2 extremes. You see on the y-axis traffic normalized by the average of the region itself. South America has the highest amplitude we observed. It's nearly 5 to 1, peak to true. Traffic explodes in the evenings and collapses overnight. And if you look at the weekends, it's clear that they are different from the weekdays. When it comes to North America, it's actually the opposite. Amplitude is around 2 to 1. The curve is much flatter. No real off-peaks. And the week is uniform, meaning weekdays and weekends also look nearly identical. They are quite similar. So they have this almost always on pattern, let's say. So within the same hemisphere, we see completely different usage cultures. Now let's look at timings. The Australian region has the earliest evening peak in our dataset. It's 8:25. They seem to be rather early to bed as well. The Middle East is quite opposite. The peak comes latest, around 11 p.m. on weekends. And when we look at late night traffic shares, the Middle East is the highest in the world. Users stay up later and wake up later than anywhere else. So both of these regions have 24 hours within a day, but it looks like their prime times differ by hours, or the way they live their lives. So we've seen that more traffic leads to more stable patterns. And this means we also establish some consistent baselines for each region. This changes from week to week, but it's usually quite similar to the point that it's almost the same. But once we have a baseline, we can also start detecting deviations from that baseline. And deviations often mean something is happening in the world. It might be an anomaly, it might be an outlier, it might be an outage. So there are three examples, three plots here that shows some interesting examples over those 2 years. So the first one is the red line is the Paris Olympics opening ceremony. And we see a traffic spike in Africa. So people obviously are streaming the ceremony itself. And it crashes back to normal at the right minute that the ceremony actually ended. If you look at the yellow line, it's about the Fortnite updates, a famous e-game that happened in Australia. And if you look into the green line, it's from South America and it's about a reality show. And the deviation clearly shows at that time where this popular show is taking place, people are streaming it. Examples such as these show that the data we're collecting is sensitive enough to capture what is happening in the world if this event has a projection in our digital lives, let's say. And the most interesting of these examples is actually this Olympics opening ceremony from Africa, this first figure. You see that the same Cloudflare radar that we referred to a couple slides before about agreeing with us and the increase in trends actually reported something the exact opposite of what we see when it comes to this opening ceremony. So they report drops in traffic of nearly up to 20%, but we see the exact opposite. So both are right. Live streaming hits the XPs. Meanwhile, other Cloudflare served content probably temporarily dropped because users just switched to watching the ceremony. And this is basically the blind man disagreeing. And that's exactly our point. A complementary vantage reveals things that other vantage points may miss. So what did we show throughout this presentation? First of all, we think the XP traffic data is credible. We've seen that the growth trends match Cloudflare pretty closely, and in some respects, blind men agree. But it's also valuable and complementary because when they disagree, we can learn unique lessons from both vantage points and why they disagree. It's also publicly accessible. As I said, the dataset is public. Our framework is still running on, and we will be releasing the dataset both for the paper and in the future. And one of our next steps as future work is, we've seen those deviation examples, but happening thousands and thousands of times. We want to build a pipeline where we can automatically detect these instances, identify them, and also annotate them about what really happened there. So building the systematic pipeline of identification and annotation and on a global scale would be our next step. And we think in our paper here, establishing those baseline patterns helps with this future work. The dataset is out there. We'll be very happy if you keep on building on it. And thank you for listening to this presentation.